Hello and welcome. In this lecture, we are going to start looking at the adjoint of an operator. This is a very important idea to go to sort of move your understanding of linear operators and transformations to the next level. We will be still sticking to R2 and C2, but still there's enough to do in this itself. I hope you get a good understanding of this. Okay, so first of all, this is a little bit of recall, but it's also slightly new. When we look at a linear transformation and we ask for the matrix of the linear transformation with respect to an orthonormal basis, it turns out it ends up being really simple. If you remember, if you have a vector v, the coordinates of the vector with respect to an orthonormal basis can be found very easily. You don't have to solve equations and all that. You simply take dot product, right? You have a vector v, you take dot product with each of the basis vectors, you automatically get the coordinates corresponding to that basis vector, right? The dot product is like the component of the vector which is along that particular direction, right? Isn't it? That's the very easy fact that we have. So now what about a linear transformation? The matrix of a linear transformation with respect to an orthonormal basis. When I say with respect to, I mean input basis is also an orthonormal basis, the same orthonormal basis is the output basis also. With respect to that, what happens to the matrix of a linear transformation? It turns out it has a very simple form. So here is the example here. Let's say you have a linear transformation T from C2 to C2. They have an orthonormal basis E1, E2. Matrix of T with respect to E1, E2, we know already what it is. You know, the first column is going to be TE1, second column is going to be TE2. Now, how do I find the coordinates of this vector TE1, okay, with respect to this basis? What is the coordinates of this vector with respect to this basis? I have to simply take the dot product. I have to take the dot product of TE1 with E1 and TE1 with E2. I get the first coordinates, right? Coordinates of TE1 are easy with respect to this. Notice how the dot product is entering the picture. So when you have an orthonormal basis and when you have an inner product in your vector space, things become really simple this way. Now this next vector TE2, again you have to find the coordinates. That's also very easy. TE2 dot E2, TE2 dot T2 dot E1, T2 dot E2. So notice how this, you have to sort of put a bracket around this TE1 so that it's, you know, T1 dot E2, E1. So remember that it's not like E1 dot E1 which will just become 1, etc. right? So TE1 dot E2, E1. So this is, so we see that the matrix itself has this very nice form. So it's T1 dot E1, T1 dot E2, T2 dot E1, T2 dot E2. Okay, remember once again there's brackets around this T1, T2. It's not like, you know, you have to do this first and then you take the dot product. Okay, so basically the point is, if you have a linear transformation T and you have an orthonormal basis with respect to which you want to find a matrix, it's really simple. It's just like all, you take the coordinates very directly and you get the matrix. Okay, so now this is one part of it. Now it turns out one can do a little bit more with this kind of an idea. Okay, so it turns out this dot product and linear operators together define something called a functional. What is this functional? Functional is any function with input as a vector or some other non-trivial quantity and output as a scalar. These things are called functionals. Okay, function usually is from, you know, scalar to scalar. That's what we think of as function. Functionals are they take more complicated quantities like vectors or something bigger and then output a scalar. So those are called functionals. Now using dot product and linear operators, you can create a functional. Okay, so that's at the heart of this whole business of adjoint and all that. Okay, so you'll see how this works. A functional f that uses a linear operator t and the dot product can be defined like this. So notice what's happening here. Instead of, I mean, I can of course look at v dot u, but that's not what I'm doing here. I'm first doing the tv. Okay, what is tv? So you take v, transform it with t first, and then you take a dot product. Okay, so if you do it, this is something like it captures some aspect of t, right? So this functional has a aspect of t and it puts out only scalars. It's not like a vector by itself. So you can see there are many aspects of t that are captured in this functional, and we try and exploit that and think about it more carefully. Okay, so this functional will play a very important role going forward. Like I said, it's basically to understand how t works, you let a vector v go through the t and then you dot it with a u. Okay, so basically you have to think of this u and v as, you know, you can now choose u and v to figure out this. So for the purposes of this functional, you have to think of u as being fixed and then you're looking at v to some scalar. Okay, so that's how we think about it. Okay, but for now, you know, we'll think of about all these guys as being you know, more generic. So this way this functional has v and u also taking part in it. Okay. So let's now do orthonormal basis. Okay. So you have an orthonormal basis for u1, e2. So I can expand u over e1, e2. So I get u1, e1 plus u2, e2. Likewise, I can also expand v. V also expands v1, e1 plus v2, e2. So notice now what's going to happen here. Okay. So I'm going to push this t inside. Okay. So I get t e1, v1 into t e1, and when I push this t inside, I'm going to get v2 into t e2. And now I use the properties of the dot product that I know. Okay. Dot product is going to be linear in the first argument and conjugate linear in the second argument, right. So if you take this v1 t e1, and then if you take dot product with this guy, this u1 is multiplying this, but it's in the second argument, so you'll get u1 bar. Okay. So you see v1 t e1 dot with e1, but this u1 which multiplies the second argument comes out as a conjugate. So you see how you got the first term. So you got v1 u1 bar. Basically, I'm going to simplify this dot product. We have a linear combination in the first argument, we have a linear combination in the second argument. So we can use both the properties of linearity in the first argument, second argument, but remember the second argument has conjugate linearity. Any scalar multiplying it will become conjugate. Okay. So if you look at the first term here, how did I get this first term? I took this first term and dot product with this second term. Okay. So this is a second argument. So this u1 will come out as u1 bar, v1 will be by itself, and the t e1 dot e1 I'll get. Okay. So I hope you saw that. Okay. So that's what I got here. Now look at the second argument here. How did I get this second argument? I took this first guy and then did a dot product with the second guy here. Okay. So when I do that, u2 becomes u2 bar here, v1 comes out as v1 here, and then t e1 dot e2. Okay. So that's all. That's all I'm doing. I'm using the linearity property to simplify this. Other two terms are also obtained in that way. v2 u1 bar e2 dot e1, v2 u2 bar e2 dot e2. So t e2 dot e2. Remember always that the t comes first, t e1 comes first, and then you do a dot product with e1. Okay. So now I'm going to do a couple of clever things here. See, notice this f of v now, thinking of u as fixed and v as the variable, is v1 times something, right, some real number, some complex number, sorry, plus v2 times a complex number. It's v1 times a complex number plus v2 times another complex number. So I can write it as an inner product of v with something. Okay. So I'm going to work towards that. I'm going to work towards writing this as an inner product of v with something. Okay. So how is that going to work? I'm going to pull v1 common out here and then write everything else I have here as the conjugate of something. Okay. I want everything else that v1 multiplies as the conjugate of something. See, that's how the inner product works. No, it's v1 times something conjugate plus v2 times something conjugate. Then that it will become the inner product of v1, v2 with that something, right. So that's what I'm going to try and do here. So this whole conjugate, so if you put conjugate here, I have to keep conjugating inside, right. So I have u1 bar t e1 dot e1. So put a whole conjugate. So inside I have to put just u1 and t e1 dot e1, I have to conjugate that. Do you see how I did the double conjugation? Hopefully you can see it. So likewise here also I have u2 by itself and then t e1 dot e2 becomes a conjugate there again. So when I take the whole conjugate here, I'll go back to this. Okay, it's the same thing I've rewritten, the same thing rewriting and observing something is a little bit tricky. It needs some careful algebra, but hopefully you can see this. Same thing I've done here, pulled v2 out and then wrote everything else that I have there under a big conjugate. So internally there was being some conjugations going on. So notice what I have here, a very nice structure inside. So this becomes an inner product of v1, v2 with what is inside, right? Now what is inside is also interesting, right? Notice what is this? This is also some sort of inner product. This is also some sort of inner product. In fact, what I have there is a linear transformation of u. Okay, so I hope you can see that. It's actually a linear transformation of u. So it's v dot with u transformed by this matrix. Okay, do you see that? Right? So the first vector here is u1 times conjugate of t e1 dot e1 plus u2 times conjugate of t e1 dot e2. The second vector here is u1 times the conjugate of t e2 dot e1 and then u2 times the conjugate of t e2 dot e2. Okay. So what you got here is very interesting. So this f of v, which was tv dot u, actually has become, once you use this orthonormal basis, actually has become v dot a linear transformation times u. Okay. Notice this clever little manipulation. There's actually not too much cleverness here. It's just carefully observing something and then rewriting it very, very carefully. So, we are able to push this TV dot u into a form which is V dot some other transform times u. Now, this transform is intimately connected to T, right? It's very similar to T in some sense, except these conjugates are occurring and there is a minor change. I am not sure if you are spotting it. There is a minor change when compared to T. So, let us see that more closely in the next slide. Okay. So, this leads us sort of to the definition of this adjoint of an operator and the connection between what is called the matrix conjugate transpose. So, previously we saw the vector conjugate transpose, now it is the matrix conjugate transpose. Remember, everything is got to do with this functional TV dot u, okay. And what is TV dot u? I have T here, which is M of T, right? What is my matrix with respect to the orthonormal basis? It is T E1 dot E1, T E2, T1 dot E2, T E2 dot E1, T E2 dot E2. This multiplying V, right? So, this is what is happening here. Then I do a dot product with U. This functional ends up being equal to V dot product with this other vector here. And what is that other vector? It is another matrix multiplying U. Now, this matrix is derived from T, but it has a special name. It is actually the conjugate transpose of this guy. Okay, so notice very carefully here. Of course, this conjugation has happened in every term, that you can clearly see. Do you see the little flip that happened here? So, notice this off diagonal terms, they got flipped. Do you see that? The diagonal remains the same, only the conjugation has happened, but the off diagonal term got flipped. Okay, it became T E2 dot E1 here down below, and then E1 dot E2 went there. So, it's what has happened here is a transposition. What is transpose? Row becomes column, right? This row, first row becomes the first column, second row becomes the second column, okay, and then conjugation has happened, okay. So, to get this functional TV dot u to look like V dot another functional, another linear operator times u, you have to do conjugate transpose. So, a matrix times V dot u is V dot conjugate transpose times u, okay. So, this is an identity, and that is a very clean thing that you get because of these orthonormal bases. If you do not have the orthonormal basis, it will not work out in this fashion, isn't it? Just go and take a look, okay. So, this matrix M of T Hermitian, as it is called, right, this M of T H, you remember from the previous lecture, this is M of T Hermitian. The Hermitian of a matrix is nothing but the conjugate transpose, okay. And of course, this conjugate transpose will also represent a operator, right. So, that is called the adjoint of T. The adjoint of the operator T is the operator which denoted T star, and that T star is the operator represented by the matrix M of T Hermitian, okay, over a particular basis. You have to choose one basis and then do this and you get it, okay. So, this is the operator. It actually does not depend on the orthonormal basis that you pick. It is a little bit subtle to see that. You will get the same operator, whichever, does not matter what basis you fix to find this transposition, okay. So, that is a slightly advanced idea. We are not going to talk about that here, okay. So, this T star is the adjoint of T, and it is an operator represented by this M of T Hermitian, okay. So, notice this wonderful little relationship here. This is a very nice relationship. This special functional that we had, TV dot u, is actually V dot T star u, okay. So, you see that, okay. So, here is a picture that will help you remember this, okay. So, you have from C2 to C2, you have V going to TV, okay, and then you do a dot product with some u here, okay. So, V went to TV and then you did a dot product with u. Guess what? There is a T star which will send u to T star u, and then you can do a dot product V dot T star u and you will get the same answer, okay. So, there is this functional that is preserved in some sense between the operator and its adjoint, okay. TV dot u equals V dot T star u, okay. So, this is true for all UV. It is like you are shifting the transformation from one part of the inner product to the other part, and for that you do the adjoint definition, or the matrix becomes conjugate transpose. I hope you see the very clean connection here, and this adjoint is a very, very important aspect. It tells you a lot about the operator. The adjoint is intimately connected to the operator, and you can learn a lot more about the operator or even a linear transformation using the adjoint, okay. Here are examples. I'm not going to go through this in detail. It's quite simple. I'll only do the last one, okay. So, the first one is very easy. 1001 is already an orthonormal basis. There's no problem here. So, you can just write 1, 2, 2, 3, okay. So, if you see the first thing here, 10 is 1, 2, 2, 3. So, the matrix you have here is with respect to 1001. So, 1, 2, 2, 3. So, the basis is 1 0 0 1. So your M Hermitian is going to be just directly 1 2 2 3, right? So there's nothing to do here. So 1 2 2 3. So you notice one very interesting fact here. So you got M Hermitian equal to M. Okay, so this may not happen all the time. In this particular case, it happened. Okay, so look at the next one. It's again 1 0 0 1. You've got 1 plus I, 2I, and then 2I 3 plus I. Okay, so you've got M is 1 plus I, 2I, 2I 3 plus I. So now if you do M Hermitian, you won't get the same equality. So you've got to do 1 minus I minus 2I minus 2I 3 minus I. Okay, so here you don't have equality on the Hermitian. So you see the general, it may not be true. In fact, the diagonals may not, off diagonals may not be equal. So you'll get very different looking ones. The second one is quite easy. The third one is a bit confusing because it says T, it's given with respect to another basis. Okay, so it says here T01 with respect to the matrix is not given directly. It's given that there is a linear transformation which takes 1 1 2 1 2. Okay, and T, I think if I read it correctly, 1 2 2 2 3. How do you do this? So can you, so it's sort of maybe tempting to say, I'll simply write the matrix and then define the Hermitian as transpose and all that, but that's not quite okay, right? So if you remember the way we derived it, the fact that we had an orthonormal basis and we did a dot product and all that was very, very crucial in the way we derived it, right? So you can't do it with something which is non-orthonormal. So this is not orthonormal, basis is not orthonormal. So it's best to find, you have to find a matrix with respect to some basis. It doesn't matter which basis you pick, it's good to pick the canonical basis. So if you want to find T of 0 1 and 1 0, that would be very good. So how do you find T of 0 1? So you have to express 0 1 in terms of 1 1 and 1 2. So let's write 1 1 1 2 times xy is 1 0, and then you have to solve for this guy. So this is just x plus y equals 1 and x plus 2y equals 0. You can subtract, you get y equals minus 1, and from there you will get x equals 2. Okay, so 2 minus 1 is one thing, and the other thing is 1 1 1 2, and then I do x y. I want 0 1 now, and that will give me x plus y equals 0, x plus 2y equals 1. You can subtract again, you get y equals 1 and x equals minus 1. Okay, so once you do this, it's very easy. So you see that T of 1 0 is actually what? X times, so 2 times T of 1 1, which is 1 2, plus minus 1 times T of 1 2, which is 2 3. Okay, so if you do this, you get 0 comma 1. Okay, that's interesting. And then if you want T of 0 1, it's going to be minus 1 times this guy 1 2 plus 1 times 2 3. So you get 1 1. Okay, so my matrix with respect to the canonical basis, which is orthonormal, we know for sure, is 0 1 and 1 1. Okay, so now you can do your favorite M Hermitian. So you will get with respect to the canonical basis that the operator is 0 1 1 1. Okay, so this is Hermitian, and then it ended up being the same, right? So you need to say M Hermitian is equal to M, and I don't know why you're getting the same example again and again, need not be true. Okay, so just watch out for these linear transformation specification, not orthonormal basis, and then you can't apply the M Hermitian directly like this, right? So this will change a little bit. So in this process, you can use any other orthonormal basis. You don't have to necessarily use canonical, and the form of the matrix you get will be something else. But then you can do a basis transform from there to here, and you'll get the same thing. Okay, so that's a nice thing to say. I'll have more to say about this orthonormal basis and basis transform later on. Okay, so that concludes our study of adjoint. I hope this was clear to you, and this is an important skill to pick up. Given a specification of a transform, how do you find its adjoint? Okay, thank you very much.